Do you ever think about going to space? We are Team U. Our team consists of 3 mechanical engineering students, Olivia, Danny, and Agostino, 2 computer engineering students, Chaitana and Naomi, and 1 software engineering student, Venki. We're a group of cross-disciplinary engineering students that came together to build a robotic wrist for the York University Robotics Society. The wrist we designed and built will be used on their Mars rover. The rover will participate in competitions against other universities to complete various missions mimicking those in space exploration. Some missions include equipment servicing and extreme object retrieval and delivery. Currently, the robotic arm that the rover uses lacks rotation in 2 axes, so the gripper is limited in terms of rotational freedom. That's where our team comes in. Our task is to design a robotic wrist to provide these missing pieces to their Mars rover.
The Robotics Society specified various requirements that our wrist must be able to perform. There are dimensional requirements such as the size and weight, interface requirements of being controlled via CAN bus signal to the teensy microcontroller, as well as functional requirements of pitching and rolling. Here's the wrist in action, meeting the requirements of the roll motion and the pitch motion. The rotations are continuous, and the wrist position can be stopped at the desired angle.
Throughout the design process, we came up with several concepts. We encountered many roadblocks, but the slack in our schedule allowed for plenty of time to overcome them. These roadblocks we encountered taught us a lot about designing a robotic gearbox, which eventually led to the cultivation of our final prototype. The prototype consists of 2 stepper motors that drive a differential gear mechanism. The mechanism can rotate the gripper in 2 directions, pitch and roll. When the motors are run in the same direction, pitch is performed. When the motors are run in opposite directions, roll is performed. Most of our components, with the exception of our metal shaft and motors, are 3D printed. Our gears are SLA printed with a high resolution, which allows the wrist to move smoothly. The remainder of our 3D printed parts are FDM printed. Our device has mounting holes at the top and bottom to allow for a seamless interface with existing equipment on the rover.
We arrived at our final electrical design through a series of calculations and trial and error. This design contains the main central unit, which is the Teensy 4.0 microcontroller. The Teensy microcontroller takes the commands given from the rover's main computer and sends them to the motors to move accordingly. To prevent any electrical damage to the motors, we use the stepper motor drivers to control the power and current sent to the stepper motors to get the precise steps required for a desired angular motion. We also used a logic level converter to allow the Teensy board and the drivers to safely communicate with each other. The entire circuit is being powered by a power supply module that simulates the rover's 4 LiPo's unregulated DC battery. All the commands being sent to the Teensy board are sent through a serial USB cable from a computer.
This flow diagram provides a high-level overview of how we met the functional requirements. The CAN bus serves as the primary communication network between the wrist and the rest of the rover. Wrist will continuously monitor the CAN bus stream for messages intended only for the wrist. Once a message is identified, other functional IDs and the informations are extracted to perform various tasks. In some cases, the wrist will transmit data to the operator via the CAN bus. This is the CAN bus message format, also known as the CAN bus protocol, where the first 11 bits carry the wrist ID and the next 8 bits carry the functional ID, and the remaining data slots contain the critical information required to perform a requested function. We have 5 main functions, each of which is formatted in a way that it can represent multiple functionalities.
The main function of the UI is to provide the users of the wrist with a simple platform where they can control the wrist without expertise in the Arduino library. The UI consists of 2 pages. The first page is a welcome page with 2 buttons, help and continue. The former gives details about our project and how to navigate through the UI. The latter takes the user to the main controller page where the user can perform actions such as motion control or movement to a specified angle. The pre-programmed commands take the rover to action with numerical input with the simple click of a button.
Here you can see the robotic wrist in action, moving along with the user input. The application of a robotic wrist is not limited to the realm of space rovers. Through adequate replacement of 3D printed parts with high-strength steel and equipment of high-performance stepper motors, the use of a robotic wrist can extend to industry assembly lines, medical surgeries, as well as household appliances. This can effectively address sustainable development goals set up by the United Nations, specifically industry, innovation, and infrastructure. With the advent of artificial intelligence the past decade, opportunities in robotic applications are endless, limited by nothing other than our own imagination. Our team worked diligently over the past 8 months with many design iterations, overcoming an endless list of challenges that came with each prototype. We're proud to share the milestone we have reached together with this Capstone project and look forward to seeing it in action in the Mars rover competition. Hopefully, it brings home the first place medal. Thank you for watching.